For most of human history, the laws of physics were built from what we could see. Our mathematical theories were grounded in the world of average-sized objects, the world directly accessible to our senses. When the telescope was first invented, we naturally pointed it towards the heavens. And we discovered that distant moons and massive planets obeyed the same laws as objects here on Earth. And so it seemed only natural to assume that those same laws would hold true when we looked inward through microscopes to the tiniest building blocks of matter. But at the turn of the 20th century, something unexpected happened. As we began to probe the atomic and subatomic world, the rules started to crumble. They didn't just bend, they broke. For example, take the electron. Strip away the wave functions, the abstract maths, the probability clouds, and just ask, what is this thing? What does it look like? And you might picture a tiny sphere of electric charge orbiting a central nucleus like the Earth orbits the Sun. And you'd have good reason, because this is what you see in textbooks. And if you zoom in on the electron, you might imagine a tiny spinning sphere. That's what the diagrams often suggest. It's elegant, it's intuitive, it's familiar. And it's completely hopelessly wrong, because in this video we're going to show that if you naively assume an electron is a tiny spinning sphere, like a planet on fast forward, then the laws of physics break down, the numbers fall apart, the model collapses, and the whole picture self-destructs. But here's the thing, this wasn't a foolish idea. It was the most natural starting point, a direct extension of everything that worked at larger scales. In 1894, Nobel laureate Albert Michelson captured the mood of the time. He said the more important fundamental laws and facts of physical science have all been discovered. Our future discoveries must be looked for in the 6th place of decimals. That's how confident physicists were. So if we want to understand why the classical spinning sphere picture of the electron fails, we need to walk through it step by step and see exactly where it leads. Let's begin with something familiar, the Earth. Now it has two types of angular momentum, orbital and spin. Orbital angular momentum comes from its yearly motion around the Sun. Any planet that orbits a star has this kind of orbital angular momentum. On the other hand, spin angular momentum comes from its daily rotation about its axis. It's the same spinning motion that causes day and night here on Earth. When I'm researching for these videos, I think a lot about how we understand the world, not just through physics, but through the information that we take in every day. How do you know that you're really getting the full picture? That's why I use Ground News. Ground News is a website and app that shows how different outlets across the political spectrum are reporting the same story. It was founded by a former NASA engineer, bringing that same level of precision and systems thinking to how we consume news. It shows each source's political bias and factuality rating. And one feature I especially like is the bias checker. It helps you analyse your own reading habits and break out of echo chambers, which is harder than it sounds. For those of us who care about nuance, whether in science or any complex topic, this kind of perspective is essential. Ground News also includes tools like the blind spot feed, which highlight stories that may be underreported in your media bubble. And if you're into science and physics, Ground News has dedicated topic pages, so you can follow what matters to you without the noise. If you're someone who likes understanding things from all angles, Ground News is a great way to stay informed and to think more critically about the world. And you can check it out at groundnews.com/physics. Scan the QR code or use the link in the description. You'll get 40% off their Vantage plan, just $5 a month, and it helps support the channel. Okay, so let's start with orbital angular momentum. For a body of mass m orbiting in a circle of radius r with linear speed v, the magnitude of the angular momentum is given by mvr. Let's now apply this to planet Earth by using the known mass of the Earth and the average orbital radius. We also know that the time it takes for the Earth to complete one orbit around the Sun, known as the orbital period, is 1 year, which is about 3.156 times 10 to the 7 seconds. We can then calculate the linear speed of the Earth using the distance travelled in one orbit, which is 2 pi r, divided by the time period, which we call t. If we then sub in our values, we find that the Earth is hurtling through space at just under 30 kilometers per second. And we can now sub this value for v, along with the mass and orbital radius, into our orbital angular momentum equation, and we find 2.66 times 10 to the power of 40 kilograms meters squared per second. Pay attention to these units, as these will be important when we consider spinning electrons. Okay, so what about spin angular momentum? Well, for a solid sphere of mass m, radius r, rotating with angular frequency omega, the spin angular momentum is given by 2/5 m r squared omega. Now, it's important to note that this equation applies specifically to solid spinning spheres. More generally, the spin angular momentum of an object is equal to I omega, where I is the moment of inertia, which is a measure of how mass is distributed within the object. A greater moment of inertia means more resistance to changes in rotational motion, just as greater mass means more resistance to changes in linear motion. Okay, so let's now apply this equation to the Earth, which has a radius of around 6,371 kilometers and a mass of 5.97 times 10 to the 24 kilograms. To use the equation, we first need to calculate the angular frequency, which is equal to 2 pi over t, where t is the time period. And in the case of the spinning Earth, this is the time for one complete revolution, also known as 1 day, and we'll take that as 24 hours. And this corresponds to roughly 86,164 seconds. And if we then plug this into our equation, we find an angular frequency of 7.292 times 10 to the minus 5 radians per second. Finally, if we sub this into our spin angular momentum equation, we find 7.07 times 10 to the 33 kilogram meters squared per second. So let's now compare the orbital and spin angular momenta for the Earth. If we take their ratio, we find a value of 3.76 times 10 to the power of 6. In other words, the orbital angular momentum is more than 3 million times greater than its spin angular momentum. And that makes sense. The Earth's orbital angular momentum depends on a huge mass, the mass of the Earth, moving at high speed far away from the orbit's centre. By contrast, the spin angular momentum comes from mass rotating around its own centre, where both the speeds and distances involved are much smaller. So even though the Earth is spinning, most of its angular momentum lies in its vast orbital motion. Now, this distinction between orbital motion around another object and spin rotation about one's own axis gives us a simple framework to extend our classical reasoning to the electron. Suppose just for a moment that the electron is a tiny solid sphere, one that orbits the nucleus like the Earth orbits the Sun, and therefore it would have orbital angular momentum. Now suppose it also spins on its own axis, like the Earth's daily rotation. Then it would also carry spin angular momentum, at least in the classical sense. So let's take that picture seriously and ask, what would classical physics predict for such a system? Now, there are several important things to note straight away, even before we do any calculations. First, the scale. We're now dealing with an object that is incomprehensibly smaller than a planet, so we'd naturally expect the magnitudes of both its orbital and spin angular momentum to be dramatically smaller. Second, unlike the Earth, the electron carries electric charge, and according to classical electromagnetism, if a charged object spins, it creates a magnetic field. That means a rotating charged sphere, like our imagined spinning electron, should generate a magnetic moment. Moreover, if we place this spinning charged sphere in an external magnetic field, the two fields should interact, and we ought to be able to predict the result. So spin, in this classical picture, wouldn't just influence the electron's own field, it would determine how the electron behaves in other fields too. And finally, we have to step back and recognise the historical moment in which the electron was discovered. Just as scientists were beginning to investigate the nature of this mysterious new particle, the very foundations of classical physics were beginning to shake. In 1900, Max Planck proposed a radical idea to resolve the so-called ultraviolet catastrophe. The idea that classical physics predicted that a black body radiator above absolute zero should be emitting an infinite amount of energy. To resolve the issue, Planck introduced the notion that Contrary to classical expectations, energy is not transferred continuously, but in discrete chunks or quanta. He proposed the relationship E equals n h bar omega, where n is an integer, counting the number of quanta, omega is the angular frequency, and h bar, now known as the reduced Planck constant, sets the scale of quantum effects. And then in 1905, Einstein extended Planck's idea to light itself to explain the photoelectric effect. Together, these discoveries laid the foundation for what would become quantum theory. But there was a subtler, often overlooked clue hiding in plain sight. The units of Planck's constant, h bar, are exactly those of angular momentum. You can see this by looking at the original relationship, E equals n h bar omega. Since n is an integer, it has no units. It then follows that the units of h bar must be the units of energy divided by the units of angular frequency. And when you do that, energy over angular frequency, you get kilograms meters squared per second. And that just so happens to be exactly the same as the units for angular momentum, whether it's orbital or spin. And it was this observation that was picked up by Niels Bohr, who in 1913 proposed a revolutionary idea in his pioneering paper on the constitution of atoms and molecules. Bohr proposed that the orbital angular momentum of an electron orbiting the nucleus could not take on just any value. Unlike a planet, whose angular momentum can vary continuously, an electron's orbital angular momentum, Bohr suggested, must come in discrete steps, in integer multiples of Planck's constant, and he proposed the simple relation L equals n h bar. It was a bold leap, but the units worked out perfectly. Planck's constant had exactly the same dimensions as angular momentum, giving the proposal a kind of mathematical legitimacy, even if no one yet understood why it should be true. But what made this idea truly remarkable was that it allowed Bohr to derive the energy levels of the hydrogen atom using a semi-classical argument, and he was then able to use this to explain the hydrogen emission spectrum for the very first time. He began by imagining an electron orbiting a proton in a perfect circle of radius r with speed v. Classically, its angular momentum would be L equals mvr, and so if we equate these two expressions and then square both sides, we get a useful equation that links classical and quantum ideas. This is the basis of Bohr's semi-classical approach. Next, he applied Coulomb's law to describe the electrostatic force between the proton and electron, which provides the necessary centripetal force to keep the electron in its orbit. If the proton has charge plus E and the electron has charge minus E, then the Coulomb force of attraction acting between these two charges is equal to E squared divided by 4 pi epsilon naught r squared. And this provides the centripetal force that keeps the electron travelling in its circular orbit, which we can write as mv squared over r, basically Newton's second law for circular motion. From this, we can rearrange slightly to get an expression for v squared, and then if we multiply both sides by m squared r squared, we obtain the following expression. And then finally, we can use the quantization relation we derived a moment ago to rewrite the left-hand side in the following form. We can then rearrange this expression in terms of the radius r, and we find the following result, an equation that tells us only certain discrete radii are allowed, and this follows directly from the angular momentum quantization condition. If we then set n equals to 1, we get what's known as the Boore radius, which is often denoted a0 and has a value of 5.29 times 10 to the minus 11 meters. That's incredibly small, but it provides a characteristic size to the atom, and the fact that this matched existing estimates for atomic size was a major triumph for Bohr's model. Bohr's next step was to use the angular momentum quantization condition to determine the energy of the electron, which is the sum of its kinetic and potential energy, and this is equal to half mv squared minus e squared divided by 4 pi epsilon naught r. Bohr then subbed in his earlier expressions for the radius and the velocity, allowing him to write the total energy in the following compact form. And when you plug in the values of the physical constants, you arrive at the simple and now famous equation E equals minus 13.6 electron volts divided by n squared. and this tells us that the energy levels of the hydrogen atom are quantized, meaning they can only take specific discrete values determined by the integer n. And this is where Boore made a brilliant leap. Boore realised that if an electron makes a transition between a higher and lower energy level, the energy it loses doesn't just disappear. It's released as a photon, and the energy of that photon is equal to the difference between the energy levels, which in turn determines the frequency, the wavelength, and ultimately the colour of the emitted light. And perhaps the greatest triumph of all was this: the wavelengths produced by electron transitions from the third, fourth, fifth and sixth energy levels inside hydrogen down to the second level all fell in the visible range, and they matched perfectly the well-known emission spectrum of hydrogen. This wasn't just a theoretical trick, it was a breakthrough. For the first time, physics could explain why atoms emit only certain colours of light. And it all came from one bold assumption: that the electron's orbital angular momentum is quantized in integer multiples of Planck's constant. That insight was so powerful and so successful in explaining the hydrogen spectrum that it naturally led to the following question: could there be other forms of angular momentum that are also quantized? In particular, what if the electron doesn't just orbit the nucleus, but also spins on its own axis, just like a planet? Let's take this idea seriously for a moment and attempt a similar semi-classical calculation. This time, we'll treat the electron as a tiny spinning sphere and use the classical expression for spin angular momentum, 2/5 m r² omega. Now, if spin is quantized in the same way as orbital angular momentum, then we should be able to equate this to n(h bar. And if we then rearrange for the angular frequency omega, we find the following expression. This seems to imply that only certain discrete angular frequencies or rates of rotation are allowed. So far so good, but to evaluate this expression we need to know the radius of the electron. But what value should we use? Well, at the turn of the 20th century, physicists didn't yet know how small the electron was, or even if it had any internal structure at all, but they did have a clever idea. What if the electron's mass came entirely from the energy stored in its electric field? That is, what if its rest energy, which is the famous mc², was equal to the energy stored in the electric field of a tiny charged sphere? To explore this idea, let's set up a thought experiment. Imagine building a spherical ball of charge very slowly, piece by piece, bringing in each unit of charge from infinity. This will require work, and if we can calculate the total work required, we can estimate the energy stored. Suppose the charge is uniformly distributed throughout the volume, with a constant charge density ρ. At some point in the construction process, we've assembled a partial sphere of radius r, and the total charge of that sphere at that moment is going to be equal to the volume multiplied by the charge density, which we can write as Q of r equals 4/3 pi r cubed times ρ, where 4/3 pi r cubed is the volume of the sphere. Now, to add a little more charge, you bring an infinitesimal amount of charge, which we label dq, from infinity, and deposit it on the outer edge of the sphere. The amount of work required to do this is then given by dw equals q of r dq divided by 4 pi epsilon naught r. And the reason is because q of r is the charge already present, and you're moving a small charge dq into its electric potential. But we want to know the total energy required to assemble the final sphere. So if we imagine the final sphere has radius capital R, then the total charge contained within this radius will be equal to capital Q equals 4/3 pi r cubed ρ. Now, since the charge is proportional to the volume, we can write the ratio of charges in the following form. And if we rearrange and simplify, we find that r is equal to the cube root of little q divided by big Q multiplied by r. It then follows that the total work done will be equal to the integral of dw evaluated from 0 to capital Q. And if we then sub in the equation we derived for r, we find the following expression, and we can then pull out the constants, which leaves us with a simple integral which we can evaluate, and we end up with the following equation for the total work done. W equals 3/5 q squared divided by 4 pi epsilon naught r. And this is the energy that is now stored in the whole field. Now here comes the bold move. Physicists asked, what if this field energy is the entire origin of the electron's mass? If so, we can equate this to the rest mass energy mc squared. And if we then rearrange for r, we find the following equation. And this provides a theoretical estimate for the radius of the electron, based on the idea that its mass arises entirely from the energy stored in its own electric field. Now, in the literature, you'll often see the numerical factor of 3/5 dropped. That's because this factor depends on the particular charge distribution model we used. So, to define a general purpose characteristic scale, physicists typically use what's called the classical electron radius, which is defined as E squared divided by 4 pi epsilon naught mc squared. Now, if we plug in the constants into this classical electron radius, we find a value of 2.82 times 10 to the minus 15 meters. And from this point onwards, we'll use this classical electron radius in our calculations, since it's the standard value quoted in textbooks and reference materials. Okay, so the question now is, if we adopt this value in our spin calculation, what do we find? Well, if you recall, we previously found that if spin is quantized like orbital angular momentum, the angular frequency should satisfy the following relation. So let's now calculate this for the case n equals 1, and then if we sub in the classical electron radius, we find an angular frequency of 3.64 times 10 to the 25 radians per second. That's a staggering spin rate, over 1,000,000 billion revolutions per second. You hear a number like that and instinctively think, that can't be right, can it? But the real shock comes when we translate this into linear speed, the speed of the surface at the electron's equator, which we can calculate easily since v equals r omega, and if we plug in the numbers, we find that in the case of n equals 1, a surface speed of 1.03 times 10 to the 11 meters per second. That's over 100 billion meters per second, and over 300 times the speed of light, which of course is a complete violation of special relativity. No part of a physical object, not even the edge of a spinning sphere, can move faster than light, and yet that's exactly what this classical model demands. Okay, so what do we do with that? We've followed all the steps, we've used perfectly valid classical equations, and we combined these with a reasonable angular momentum quantization condition that proved very fruitful within the context of orbital angular momentum and the Boore model. We also assumed a finite radius for the electron that physicists of the early 1900s often used, the so-called classical electron radius, and we ended up with a result that's physically impossible. So perhaps the problem lies in that assumed radius. So maybe instead of accepting it, we should ask, what's the minimum radius an electron would need in order that its surface speed does not exceed the speed of light? Well, we can answer that by using the surface speed equation we just derived. We see that a larger radius would give rise to a smaller surface speed. In fact, if we require that the speed at the surface is less than the speed of light, then we see that the radius must be greater than 5 h-bar divided by 2mc. This gives the minimum radius required for a spinning electron to stay subluminal, and if we plug in the constants, we find a value of around 10 to the minus 12 meters. Now that might sound minuscule, but on subatomic scales it's a monstrosity. Consider this. The radius of a proton, the building block of every atomic nucleus, is around 10 to the minus 15 meters. Even the radius of the largest nuclei, like uranium, are around 7 times 10 to the minus 15 meters. So this minimum radius for a spinning electron is over 100 times larger than the largest nucleus. Not just slightly oversized, but grotesquely oversized. If electrons really were this bloated, the very foundations of atomic structure would collapse. Okay, fine. So maybe the electron isn't extended. Maybe its mass is truly concentrated at a single point. But now we hit the opposite problem. Spin angular momentum, in the classical sense, comes from mass rotating around a central axis, but a point has no internal structure. There's nothing to rotate. And if we look at the classical spin angular momentum equation, we see that if r goes to 0, then the spin angular momentum also goes to 0. And so this would seem to imply that a truly point-like electron can't spin at all. And yet, despite the contradictions, the impossibilities, and the violations of relativity, experiments in the early 20th century showed that electrons do behave as if they are, in some sense, spinning. They act like tiny bar magnets, magnetic dipoles that respond to external magnetic fields. Place them in a magnetic field and they precess, like a quantum gyroscope, in a way that we can measure with astonishing precision. These effects aren't vague or qualitative. They're among the most precisely confirmed properties in all of science. The electron's magnetic moment is one of the most precisely measured quantities in all of physics, known to better than 1 part in a trillion. But there's a twist. The kind of spin we observe, while it may resemble classical rotation, is in fact something radically different. So different it forces us to rethink the very nature of the microscopic world. Experiments such as the anomalous Zeeman effect and the Stern-Gerlach experiment couldn't be explained using orbital angular momentum alone. They revealed that particles like electrons possess a new kind of internal angular momentum, one that doesn't come in integer units of h-bar, like orbital angular momentum, and like we've explored throughout this video, but instead in half-integer units. Particles with this property are known as spin-half particles, and electrons are the most iconic example. In the next video, we'll peel back the final layer and uncover what spin really is, and how, from the wreckage of classical physics, a new kind of angular momentum was born. So, thank you for watching, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following, who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.